In this discussion video, we'll do an optimization problem involving a wire forming a square in a circle. So it says a wire of length 10 inches is cut into two pieces. One piece is shaped into a square and the other is shaped into a circle. Find the minimum and maximum total area. So I want to first give you 7 minutes to try this problem. It's probably not going to be enough time to finish the question, but definitely take those 7 minutes to try it. These optimization questions can be challenging. And if this is a topic that is a little bit more difficult for you, it's super important to engage, especially with the topics that we feel weaker with. That is super important to growing. So pause it in 4, 3, 2, 1. Pause it for 7 minutes to try this. Alrighty, so hopefully you did that. Hopefully you paused it and tried it for 7 minutes. Even if you got stuck and you struggled with it a little bit, hopefully you persevered and kept on trying things. Okay. So let's talk about it. So we want to minimize and maximize area here. So we are trying to optimize. I want to do both, minimize and maximize. Optimize the area. Okay, and I think we can draw a picture. So it says that we have this wire. The length of it is 10 inches, and it gets cut. I don't want to assume necessarily that it cuts exactly in half. So maybe it gets cut off slightly to the side, and I don't know the length of each piece, so maybe I'll say one piece is length x and the other piece is length y. So we're assigning some variables to quantities that we don't know. And then one of the pieces is bent to form a square. So maybe this first piece will be bent to form a square. And then the second piece is bent to form a circle. Okay, so x would be the perimeter of the square, which means each of the sides of the square is going to be x divided by 4. All of these are going to be x divided by 4. So the y is going to be this whole distance around the circle. That is the circumference. So the circumference of the circle is going to be y. Okay, so if I just draw in maybe the radius here. So we get this, at least this tentative picture right now. Now let's write an equation for the thing that we want to optimize. In this case, we call this the objective. In this problem, we're trying to optimize the area. So we'll write an equation for, let's see, the total area. That means we got to add the area of the square, which is going to be x over 4 squared, to the area of the circle, which is pi r squared. Alrighty. The other thing that I want to keep in mind here is, although it says this wire is cut into two pieces, technically it's okay for x to be equal to 0 and y to be equal to 0. These are okay. If one of these pieces had a length of 0, that would make that shape be a degenerate shape, which means it's actually going to be a dot here. So the square would just be a point, or the circle would just be a point if that happened. But that's okay. We're considering that to be a valid shape. All right, so we have this objective, and now let's try to form a constraint. So a constraint is another equation that relates the variables in our objective. So we know that x plus y, the total length of the wire, is 10. The issue that I see with this is there's this other variable r in the objective. Not just an x, there's this variable r. That's where the circumference is going to come into play. Remember, the circumference is 2 pi r, and that equals y. So if I isolate r is y over 2 pi. So let's take that and let's plug that into our objective equation. So x over 4 squared is x squared over 16. So x squared over 16. And then we get plus pi r squared. R squared is going to be y over 2 pi being squared. Okay, so now that we have this, let's isolate one of the variables in the constraint so we can plug into the objective to get the objective in terms of one variable. Okay, so if I isolate y, we get y equals 10 minus x. I could also isolate the x. I would say both of them are equally easy to isolate here. And if I plug these into my area, we get x squared over 16 plus, we get pi times y squared is going to be 10 minus x squared. And on the denominator, we'll get 2 pi being squared, which is 4 times pi squared. All right, so we can simplify. We have area equals x squared over 16. And if I cancel one of these pi's, I'm left with, on the numerator, 10 minus x squared over, on the denominator, 4 pi. Okay, so we got our area in terms of one function. Now we are ready to take a derivative. So we'll take the derivative with respect to x, that's the variable on the right. So if we do that, we get a prime, the derivative of a, is going to be x over 8. When that 2 comes down, I get x over 8. And then on the next term, we do chain rule. So the 2 will come down. I'll get 2 times 10 minus x. We can keep the 4 pi on the bottom, because that's just a constant. It's just a constant dividing this thing, so it can just stay there. But then I do the chain rule, and I multiply by the derivative of the inside, the derivative of 10 minus x, which is negative 1. All right, so we have a prime equals x over 8. And now, let's see, if we distribute, so 2 times negative 1 is negative 2. If we distribute negative 2 to the 10 minus x, we'll get negative 20 plus 2x, and this whole thing over 4 pi. Okay, so that's my derivative. I need to be able to simplify this so I can set it equal to 0 and figure out when it's undefined. So with this, I have a fraction plus a fraction. Let's get a common denominator. So the first fraction I'll multiply by pi over pi on the top and bottom. The next one I'll multiply by 2 over 2. So that gives us a prime equals x pi over 8 pi, and then plus negative 40 plus 4x over 8 pi. So now we can combine these and get a prime equals, we get x pi, I'll put plus 4x minus 40 over 8 pi. Okay, so now when is this equal to 0? My derivative equals 0 when, because I have this one fraction, for that fraction to be 0, I need the numerator, which is pi x plus 4x minus 40. I need the numerator to be equal to 0. So let's factor an x out of these two terms to give me x times pi plus 4, and move the 40 over. And then I could divide the pi plus 4. So we get x equals 40 over pi plus 4. Okay, and then for this to be undefined, the denominator would have to be 0. But the denominator is 8 pi, and that's definitely not 0. It's never going to be 0. So my derivative is never undefined. So we have our critical number. It's 40 over pi plus 4. We're ready to test it. Okay, so we are ready to test our critical numbers. Okay, so let's first just state the interval for our variable. So we got our function in terms of the variable x, because we got our area completely in terms of x. And x was the length of one of these pieces. So the smallest that could be is 0. And if it was 0, we'd get a degenerate situation for one of the shapes, for the square. And the biggest it could be is 10, and that would make the circle be a degenerate circle. Okay, so x is greater than or equal to 0 and less than or equal to 10. Okay, so let's use one of our 3 ways to test our critical numbers. Okay, so for this problem, I'm going to look back to my first derivative. Okay, so here's our first derivative. This first derivative is actually, it's a linear function actually. This is actually the equation of a line. So the second derivative is actually going to be very simple. Let's do the second derivative test on this. Okay. You might be recognizing, wait, this is a closed interval. Couldn't I just do the closed interval test? And I could, but let's just say, I didn't see that. Let's do the second derivative test. Second derivative test. Okay, so I take the second derivative. So for the second derivative, looking back to my first derivative, this 8 pi on the bottom is just a constant. So I can pull that in front. I'll get 1 over 8 pi. And then times the derivative of this stuff on the numerator. So the derivative of x pi is pi. Derivative 4x is, I'll get a plus 4. And the minus 40 will be 0. So that's my second derivative. Okay, so there's my second derivative. And I notice this is a positive number. So my second derivative is just greater than 0, no matter what x is. So if I were to draw a picture, so my critical number happens to be at, 40 over pi plus 4. So we know that we have a critical number there. And because my second derivative is positive, we know that the graph is going to be concave up there, which will give me a local min. So I have to give a little bit extra justification to explain why is this an absolute min. So we would say since our second derivative here is greater than 0 for all values of x, the local min min that we have at this x value, at x equals 40 over pi plus 4, is, because what this tells me now is the graph is going to look like that, concave up the whole way. And if it looks like that the whole way, this has to be an absolute min. It has to be an absolute min. So the question wanted to know, what is the minimum area? At least that's part of it. So let's recall our area function. Our area function was x squared over 16 plus, that was 10 minus x squared over 4 pi. So our min area, our minimum area, is going to be this when I plug in 40 over pi plus 4. So we'll get 40 over pi plus 4 being squared over 16, and then plus, I'll get 10 minus 40 over pi plus 4 being squared over 4 pi. And the units in this question for length were inches, so for area are going to be inches squared, and that is my minimum area. Okay, but this question, remember, wanted the minimum and maximum total area, and I just got the min. So where's the max? If I look at my picture, the only place the max could be is at one of the endpoints. And that's okay. It's okay for the max to be at one of the endpoints because I have a closed interval. If I had an open interval, I would have something like, oh, and then there's a hole. And if there's a hole like that, I never actually reach that value. But because it's closed, it's going to be something like, oh, maybe it's closed here, and maybe on this side it's closed a little bit higher, at a higher y value, and that would give me the max. So the moral there is that the absolute max must occur at one of the endpoints based off of our work so far. So let's test the endpoints in our area function. So the endpoints of our interval were 0 and 10. So I'm going to plug in 0. I'm going to plug in 10. If we plug 0 into this, we'll get 0 squared over 16 plus 10 squared over 4 pi. Let's write that 16 better. 16. So this is 100 over 4 pi, which simplifies to 25 over pi. If I plug 10 in, we will get 10 squared over 16 plus 0 squared over 4 pi. So this becomes 100 over 16. And if you divide the top and the bottom by 4, that's 25 over 4. Okay, and comparing these two values, they have the same numerator, but the pi on the denominator is smaller, and that makes this the bigger fraction. So this is going to be our maximum area. Our maximum area is 25 over pi square inches.